Okay. At the end of class, just come up and give me your name and I'll give you your test back. All right. And while we're waiting for the last few people to come in, find me the derivative.
$16x squared plus 40x plus 6.
I don't know. I haven't done it. But it sounds right.
Or 24.
24, actually. As you bring down the 3. So 8 times 3 is 24. So yes. You multiplied wrong. You multiplied wrong.
Oh.
8 times 3. You bring down the, because it was 8x to the third.
Oh. Goodness, you're right.
It's okay.
I brought-
Easy
I
little
brought-
mis-
I brought
you
the
brought-
2 down.
Yeah,
My bad.
easy little mistakes to make. All right. So what was the rule that we talked about last class? We did the power rule. And so the power rule was if f of x is x to the n, f prime of x is n x to the n minus 1. So as this problem is stated right here, can we do the power rule? No. So we have to FOIL this out first. So FOILing this out, we get 8x to the third plus 20x squared plus 6x plus 15. Now can we do the power rule? Yes. So I get 24x squared plus 40x plus 6. So the power rule works when I have it in that form. That's the only thing the power rule does. The original problem was a product. So what we're going to look at today is we're going to look at the product and the quotient. You're going to notice that there's going to be quite a few problems that you'll be able to do multiple ways. Okay. We're going to actually do this problem again as the product rule just so you can see that it comes out to be the same answer. Sometimes one way is going to be easier than the other. Sometimes foiling this out is going to be easier and working it with that way. Other ways, you're not going to be able to. When you have your final questions and your test or quizzes and homework and everything else, you just have to decide which way you want to do. Okay? You can do things multiple ways. That is fine. I'm not going to say you have to use this method to do a certain problem. You can do it any way you want, as long as you get the right answer and everything you do is mathematically correct. The product rule. It is the derivative of the first times the second plus the derivative of the second times the first. So when you're looking at the product rule, so write that rule down. We need to have two functions that are multiplied by each other. Both those functions have to be differentiable on their own. So you have to be able to find the derivative of fx, you have to find the derivative of g of x. If you cannot find the derivative of one piece, the whole derivative fails. Okay. So it's the derivative of the first times the second plus the derivative of the second times the first. You will see in the book, they just have it reversed. They have the f of x, g prime of x first. It doesn't matter, it's addition. The reason I like writing it this way is the quotient rule is exactly the same process, basically, except for it has subtraction in it. And it's easier to remember one root, always do the derivative of the first one first, than to try to remember doing it two different ways. All right, so we're back up with that problem back up. We're going to do this one again. All right, so let's look at this problem again. What's f of x? So when we're looking at it in terms of the product rule, the f of x is the first multiplication, the g of x is the second one. What's f prime of x? Eight x. What's g of x? Which the derivative of g of x, g prime of x, is 2. So it's the derivative of the first, so 8x times the second. So we've got f prime of x times g of x plus f of x times g prime of x. So we've got 16x squared plus 40x plus 8x squared plus 6, which equals the 24x to x squared plus 40x plus 6. So the answer comes out to be the same both ways. And it should. If it didn't, we did something wrong. So I don't think this one is any harder mathematically than the doing it out with the power rule. It's just a matter of personal preference in that respect. Sometimes it's easier to do the quick foiling.
Can you do this with more than 2?
Yes. You'd end up having, actually, you know what? I'll show you one of those. So we'll do one with 3. All right. Any questions with this? Okay. Let's look at a couple more. Let's do one that's not one we can just FOIL out. So we've got x times e to the x. Yes. Huh? What is it? No. Yes, that is absolutely true. And if it was the product rule was just find the derivative of each piece, you'd be correct. But the product rule is not. So I really hate the fact I used f of x here, but that's okay. Yeah, I don't want to use u because that's u substitution. All right, we'll say m is x. So if m is x, what's m prime? What's the derivative of x?
1.
1. Lot simpler than you were trying to make it. Because remember, so when you're looking at this, we want to split this up. We have a product. We have two things that we're multiplying. So if m is x, m prime is 1. If n is e to the x, what's n prime? That's e to the x. Because remember, we talked about that the other day. So the derivative of e to the x is e to the x. So it's the derivative of the first, so 1 times the second, plus the derivative of the second times the first. So m prime times n plus n prime times m. So this would be x to the first power, correct? Yeah. So bring that down. So that's the 1. Subtract 1 minus 1 is 0. X to the 0 power is 1. That's how that became 1. The derivative of e to the x is e to the x. That one doesn't change. So the product rule is looking at, we have a product of something. In this case, the product is, so you can write it like this if it's easier to see. We have two things we multiply. That's not one piece. That's one term, but we break it into factors. So we have the x and we have the e to the x. So that's what we're looking at when we're looking at the product rule. This one was a lot easier to see, the separation. Yeah. So, but sometimes it's not going to be broken down by parentheses. You still have to look at it as two separate pieces. So if we clean this up a little bit, I have e to the x plus e to the x times x, which I can pull out the e to the x and I end up getting 1 plus x. So that is my derivative.
Where does 1 plus x come?
I pulled out the e to the x. I factored it out. So this would be just 1 because I pulled it out, and that would be just the x.
Do you do that though?
No. I did it for a reason, but do you have to? No. Both those would be the exact same answer. Find me the second derivative. I changed it to M so you can use F and G. Don't use M squared.
Oh, numerals.
That'll cause you trouble later on when you look back and go, why is M squared this? Yes. Huh? That's not the answer. There's more to it than that. It's okay. We'll go over it again. So, step one, find me what f of x and what g of x. Find me those two things. I specifically changed it to f, so you can use f and g. Yes. So step one is find what f of x is and what g of x is. Once you get those two, you can find f prime of x and g prime of x.
G prime x just one.
This is why I did the factoring, so I could actually do it this way. So f of x is e to the x, and g of x is 1 plus x. Once you got those, look for the derivative of each one of those. Derivative of e to the x is e to the x. Derivative of 1 plus x is 1. So then I have the derivative of the first, which is e to the x, times the second, plus the first, or the derivative of the second, times the first. So e to the x plus e to the x, or x e to the x, plus e to the x. So I have e to the x and then 2 plus x. Yes, no.
Did you skip this step?
Yeah, it's 1 plus 1 is 2. I just put them together at the same time.
Well, you would, yeah.
Yeah, it'd be 2. So this, you could write this step as 2 e to the x plus x e to the x, which is how I got the 2 plus x.
This constant was increased by one.
In this specific function, yes, it does. So in this specific function, what ends up happening, if I was to look for the third derivative of this one, this does not always work. It's just a specific function, but I want to show you something. The next one's actually going to be 3 plus x. So that would be the third derivative. So I noticed on one person's paper, and I didn't see anybody else, but one of the very specific things is when you're writing your terms, making sure how to write them correctly. So the first derivative is just a single prime, second derivative is 2. The third derivative is 3 primes. After that point, you no longer have to write primes. You actually write it like this. You put it in parentheses. So anything after the third prime, you'll see like that. So that'd be the fourth derivative, and then the fifth derivative would be like that. So the fourth derivative of this would be plus x. The fifth derivative would be 5 plus x. That does not work for every problem, this specific one. But that's how you'd write your derivatives as they keep going up. If you see something like this with an n, that means the nth derivative. So it's just like it basically keeps going on forever. Okay. It was just a really good problem for me to show you the notation piece there. Let's do. Yes.
So for something like that, with the derivative, like where the numerator, it's like, 5 is 5, 6 is.
Yeah.
Is there a certain way that? Or, you know what I'm trying to say, like, instead of,
What, the pattern?
yeah,
This one ends up being this.
oh, that's how you write it?
Yeah.
Oh,
Do you prefer if we factor it out?
So in this one, the reason I factored it out was because I wanted you to do the next derivative and I wanted it as a product. Could you have done the product? Could you have done the next one with just this? Yeah, you'd have found the derivative of that. You'd have had to do this as separate. So you'd have found the derivative of that piece first and then found the derivative of the x plus x because that's now a product. And you should have realized it's the exact same thing you started with and gotten that. But yeah, you don't necessarily have to multiply it back out or factor it out to do it. It just depends on what you're going to do after that point and how it's going to help you. No, and that's in the test that won't matter at all. Let's do. I want you guys to do one more. I want to find one that's. Let's do this one. All right. I'm going to tell you, I want it done with the product rule. I do not want you multiplying it out. Even though, yes, you could absolutely do this one with the power rule. I want you to use the product rule. I want you to practice it a little bit. one of the things that I would suggest is write it like I just wrote it. Write down your f of w, write down your g of w, write down the derivatives. Don't try to go directly from the problem to the rule. Okay? Sometimes when you do that, you miss things and you can get things mixed up. Writing down those pieces there will be helpful to you, and then plug into your rule. Okay? Especially when things get more complicated and we start to add more parts and stuff like that to it. Sometimes taking a step back and writing a little more at the beginning is going to be helpful for you. Yes.
Taking it to like negative 1 w or negative 1 over w squared to like
I wouldn't until the end. Because remember, we're gonna have to multiply these things and stuff at some point, like to clean them up. So I wouldn't worry about the negative exponents until the very end. Because they might take care of themselves.
You multiply.
Mhm. When you multiply like bases, what do you do with the exponents? Right. So 2 plus negative 1 is? Right. So it's the derivative of the first, so 2w plus 3 times the second plus the first. I've been putting the derivative of the second first. So negative w minus 2 plus 4w to the negative fifth times w squared plus 3w. So 2w times w to the negative 1 is just 2. Because 1 minus 1 is 0. 2w times w to the negative fourth is 2w to the negative third. Plus 3w to the negative first minus 3w to the negative fourth. Plus negative 2w, or negative w to the negative second times w to the second is just negative 1. Minus 3w to the negative first plus 4w to the negative third plus 12w to the negative fourth. I know, a bunch of problems. Which is why I said don't change them to fractions, because it would make it even messier. Yeah.
3w times w.
Wait,
You do the 1 minus.
this,
Yeah.
bring down the 2, subtract 1. The w cancels itself out. So I got 2 minus 1, which is 1. So we're done with that one, done with that one. 3w negative 1 minus 3w to the negative 1, those cancel out. Negative 2 plus 4 is 2, so plus 2w to the negative third. Here are those two. And then plus 9w to the negative fourth. That takes care of those two. Which we then can write as 2 over w to the third plus 9 over w to the fourth.
You may have to change it to that.
No, because the original problem had negative exponents in it, so you don't necessarily have to. If the original problem did not have negative exponents, I don't want negative exponents in the answer. But I will tell you, some teachers are really picky about negative exponents. So all right. All right, let's look at the product rule. Or the quotient rule, I should say. Here is the quotient rule. So, and you can do f prime of g, which if you look right here, that is exactly what we were just doing as the product rule, except it's a minus instead of a plus. That's the reason I wrote it that way. So the only difference between the product rule and the quotient rule is we're subtracting the top. And I have a division. The bottom becomes that, whatever it was on the bottom, squared. All right, so let's look at this one. So, first step, just like we've been doing for the product rule. Find me my f prime, or my f, and my f prime, my g, and my g prime. So your f is going to be your numerator, your g is going to be your denominator. Just like when we were looking at the product, the f was the first one, the g was the second one. So with f prime, and with g prime. Yep. So remember the rule, f prime g minus fg prime over g squared. So we've got 2x plus 1 times x to the third plus 6 minus x squared plus x minus 2 times 3x squared all over x to the third plus 6 squared. So you can start to see how this setup here really helps do this, because the problems are going to get more complex. And having that set up so you have the pieces that you need to plug in will definitely make your life a lot easier.
Excuse me, Professor.
Yes.
Isn't it 2x to the negative 1?
Why?
Because the x would just be a 1 and the oh, I'm sorry.
That disappears.
I forgot the -2 becomes a 0.
Yeah,
Thank you.
no problem. All right, so now we've got this. Now we just got to clean it up. This piece right down here, in most situations, you can leave that as is. You do not have to multiply that out. Just leave it that squared. Okay. So we're really just going to look at the top to simplify it on the top. So I've got 2x to the 4th plus 12x plus x to the 3rd plus 6 minus 3x to the 4th plus 3x to the 3rd minus 6x squared. Notice how I left them in parentheses. Very, very, very common mistake. I have a minus sign there. I have to distribute that minus sign through. If you forget your parentheses, odds are you're going to forget to distribute the negative sign through, which means the signs of these two problems will be wrong and you'll have the wrong answer at the end. Okay, so it's a good habit to get into to leave those parentheses there until you've dealt with the negative sign. So this becomes negative 3x to the 4th, negative 3x to the 3rd, plus 6x squared. So I have 2x to the 4th minus 3x to the 4th, so it's negative x to the 4th. I have x to the 3rd minus 3x to the 3rd, so that's negative 2x to the 3rd, plus 6x squared, plus 12x, plus 6. All over x to the 3rd plus 6 squared. And that's my final answer. The other thing you want to do is while you're going through, notice my exponents are in order. It's a good habit to get into doing that. This way you're not going to miss things going down the row. So look for your highest exponent first, then the next highest exponent. All right, because it's really easy to miss things when you have this many terms to look through. That's it. Huh? No. We still have some problems to do. But I've done the two rules. Those are the only rules we're learning today. So everything after this point, we're just going to do some problems so you can practice those rules. But we've done the product rule, we've done the quotient rule. I'm done with teaching you new materials. All right, let's look at this one. So the very first problem that we did for the product rule was the same as the very first problem you did when you walked into class. When you walked into class, you FOILed it out, used the power rule to find the derivative. And then I showed you how you could do the product rule and get the exact same answer. Depending on which way you want to do it, sometimes it's just going to be just as easy to do the product rule as it is to do the FOILing it out first and doing the power rule. The quotient rule is a little more complex because there's subtraction in there, there's division in there. So you really do want to look at your problem first to see if there's a way to simplify it. Okay? So in this problem, there's nothing that I could cancel out to factor this out, to make this simpler. So we kind of have to do the product rule. This problem, I only have an x down the bottom. So I could split this problem up. I could write it as 3x squared over x plus 2 squared of x over x. Because remember, division, I can, as long as I put the same thing underneath everything on the top, I can do that. Because it's just an x, I can then change this to 3x. And remember that your square root is really the same thing as saying x to the 1/2. So this would be 2x to the negative 1/2. Because I do the 1/2 minus 1. Now what rule can I use? I can use the power rule. I don't have to use the quotient rule for this one. So my derivative would be 3 plus 2 times negative 1/2 x to the negative 3/2. Yes.
There's a 3x plus the 2x to the negative. Where'd you get the negative?
That's x to the first.
Oh,
You're fine. And that would be my final answer. That's a lot easier to do than doing out the quotient rule for this one. The quotient rule would end up giving you the same answer, but you'd end up having to simplify a lot more down at the ends. Some problems are not going to be as obvious as that. Like, let's do. So x squared minus 5x plus 6 divided by x minus 2. Yes. We can use the quotient rule. We could. But let's factor the top. What two numbers multiplied at positive 6 and added negative 5? That would give me a negative 6. So in this case, it's negative 2 and negative 3. So now I'm just looking for the derivative of x minus 3, which is just 1. Okay. So that's why. Could you do the quotient rule at the beginning? Absolutely. Is it going to look that nice? No. So, like, this one was a little easier to recognize that you could break things up than this one, but always look for those opportunities first. Okay? So, yes, you know the product rule. Yes, we're going to use the product rule when we have division. Don't forget your algebra. sometimes simplifying the problems down will make your life a lot easier. And I will tell you, in derivatives, there's a lot of different ways we can do things, and they're all going to end up working out to be nice at the end for the most part. In integration, which is what we get to towards the end of this class, and which we're going to do in Calc 2, simplifying the problems is going to make your life tremendously easier. Like to the point where sometimes you can't do the problem as it's stated without simplifying it down first. Okay, so always look for opportunities to use your algebra to simplify a problem down first. All right, and this problem made your life a lot easier. So, all right, so let's have you guys do one with a quotient rule. Let's have you do.
What would happen if you had a crash after another crash? Where what do you do with that? Like how we had it.
If you had like that,
Yeah.
I'd multiply them together first.
Could you send if you have prime and g prime and then do each one separately though?
Yes. But then you're going to have a quotient. So if you did, all right, so if you did it like we did before, now you have to do that derivative. That's not a, well, this one you can change it to 3x to the negative 1 to do the power rule for. G is going to be x plus 2 over x to the third. And now you have to do the derivative of that. So it just makes it a little more complex sometimes. In this case, I would have done this and then broke that up and did it. So I would have changed that to there, and then I would have done three x to the negative third plus 6 to the negative fourth, and then just do the power rule on it. So again, it all depends on what the problem that you have is, and do as much algebra as you can to simplify the problem down before you try to do your rules. All right. I'll have you guys do this one. And don't worry, I didn't forget your question about doing 3. So we'll do a couple things like that. All right, find me the derivative of that. Now I probably should put something in front of it. Let's make it m equals. Technically m of equals.
That's one, right? That's fine. T minus one. T again.
Yes, it's -1.
Thank you.
I haven't done the F yet, so I don't know. It just seemed weird that it was just 5. So you've got so you'll notice when I do these problems out, I'm gonna ignore the bottom because we know what the bottom's gonna be. It's just that square. So let's just worry about the top piece. It makes my life a little bit easier when I'm writing things out. It doesn't? Okay. It looked weird.
Yeah, I mistook, one.
Oh, okay. So I have 5t to the third minus 15t squared minus 5. All over t to the third minus t minus 1 squared. Oh, you're right, it is. Good catch. The beauty, oh, hold on. So I've got negative 10 to the third, t to the third, minus 5. Yeah, good catch. All right. All right. So we estimate the rate at which total personal, we want to figure out what the rate of total personal income is rising in Boulder, Colorado. Okay. So how would we figure out the total personal income of a city? How would I figure out the income of this class? So I'd ask everybody their income, and then I would do what? I'd add them all up, right? Okay. So I could do that in this class because I have different people. Let's say the average income in this classroom is $30,000 a year. Okay. So how can I figure out the total income of this classroom? 30 times however many people's in the classroom, right? Okay. So if there's 30 in the classroom, that means the total income of this classroom is $900,000. Yeah. Money adds up quick. Like you don't actually realize like how fast things add up. Yeah. It's like things add up quick. All right. So to figure out the total income for Boulder, Colorado, I'd have to multiply their population by their income, correct? Okay. So I would do population times income. But they're asking at what's the rate it is changing. So what are they asking for? They're asking for the derivative of it. Because the derivative is going to give me the rate of change, correct? Well, what's derivative? It's slope, right? That's telling me how fast something's changing. So that's why I actually really like this problem. Because so we think about, we've done a lot of algebra problems basically. But you can really apply this stuff. So whenever we're looking at derivatives, we're looking at slopes. And slopes are just rate of change between two objects. In most real life situations, one of those will be considered as time. And then it's how fast the money's changing based on time, or population is changing based on time, whatever it happens to be. So they're just asking, what's the derivative of this? But they didn't give me a formula. So I can't go through and do what we've been doing. So if this was my problem, I'm doing population times income, what's my derivative of that? I think that's a what? That's a product. So what's the product rule say? So it's the derivative of population times income, right? Plus, right. So population times the derivative of income. Right? That's just the product rule, correct? So I just need to find those four things. So what's the population? Population's 107,350. What's the population derivative? Right, because that's the change, correct? That's 1960. So that's my population. That's my population change. Everybody understand where I got those two numbers? Do you understand the connection between those and the product rule? We're looking for what our population is, and we're looking for what it changes. The change is my derivative. So now what about income? Right, 60,220. And what's it changing by? So that is my derivative. So does everybody see where I got those four numbers from? Okay. So now I have those four numbers, correct? What's the change in population, or the derivative of the population? 1960. What's the income? What's the population? And what's the derivative of the income? So now I can multiply those. It is a big number.
So what is that?
What does that number mean?
What's the problem?
Roughly how much?
That's the rate of change.
That's roughly
There's
how
no
much
way.
money,
That's how much it's gone up.
Boulder, Colorado
2000.
makes total.
15. That's how much it's raised, 2015.
So,
Oh, that was their, all the people's income?
yes.
Oh, yeah.
So that is my change in population over time. So this was 50. Wrong section. Yeah. So why? So it's almost what? Almost $360 million? Yeah, just about $360 million. Who would care? Yeah, the town would care, right? So if they know that the income of their population is increasing by $360 million a year, and their tax rate is, say, 5%, they can estimate the income, the amount of taxes that they're going to be collecting that next year. Okay. In addition to what they already had, that would help their budget. Right. Like, and that's why I was like, when I did this room, I said if there were 30 people, it's $900,000. So if you think about like, okay, $360 million, like to people who you guys do, who don't make that much money, that's an insane amount of money. But when you're talking about a budget for a town, and you're talking about just over 100,000 people, like that's not nearly as much as it sounds. Yes. That's the change in income. So over the course of a year, they're going to make an additional $360 million. whatever whatever their income was the previous year. Yeah. If we wanted to find out what just their income was, we would just multiply their population times their income. So you could do 107,000 times the 60,000, and that would give you their income.
Is this real numbers?
Probably pretty close.
People do this in real life. They go to towns and they just solve stuff like this, figure out.
Well, no. Random people don't wander around trying to figure this stuff out. Like, even most people don't just randomly go around to town to figure this stuff out. However, there are people known as consultants who make lots and lots of money to go into a town and go into a business or go into an organization, whatever it happens to be, and help them with this. So towns and states and everything else pay consultants a lot of money to figure out how to spend their money or how to bring in more money or bring in more revenue. So there are people who get paid to do this. They're just not random people. Yes.
So when I get my tax rate, I check. Take my loss for that. But like, I don't work in the town I live in. So,
Okay, so we here do not have town income taxes.
yeah.
We have state income tax. So it doesn't matter where you live in the state. So you pay the state income tax. If you work in Connecticut, but you live in, say, Westerly, Rhode Island, you are paying Connecticut income tax because you're working in Connecticut and that's where you're getting charged. But you have to file Connecticut income tax and Rhode Island income tax.
How does that work?
It's a nightmare. And there's probably, I guarantee if you talk to your friends, there are people who have to do that because there are people who I know who live in Westerly who come here. So it's a nightmare. Like I went to college in Massachusetts, so I worked in Massachusetts when I was in college. But when I came home, I was working in Connecticut, so I had jobs in both states, and I had to file income tax in both states. It was a nightmare. And it's actually becoming a bigger problem now because of people who do remote work. So depending on how your company is charging, you could be working for a company in New York City, for example, but living in Connecticut, doing all your work in Connecticut. Yeah. So what they should be doing is they should be actually charging you taxes in the state that you live in.
I owe the state money.
So yeah, that's the problem.
Simple fix is don't file your tax.
Oh, I was gonna say, wait till you start thinking of super, get all back.
All right. So that's where this stuff is actually really used. But notice we didn't need the functions and equations and everything else to do this problem. You can do it straight out with just the information they gave us using the product. Okay. All right.
Oh, David.
All right. Since you love word problems, here. Let's do this one.
Yo, guppies,
Yeah.
reproduce like crazy.
Yes.
Guppies are,
Yeah, they're just little fish.
they're really interesting to watch, especially when they're treated.
Wow.
You'll have two guppies in the tank, you give it a lunch, you'll have 500. They eat each other.
What are we finding?
Well, they're good.
Anytime
You do
soon?
rate of change with logarithms
So, like,
too?
my butterflies,
Yeah,
That was kind of
we'll get there. I need to do a little more before we start dealing with logarithms and exponential, like the bigger exponential functions. We're gonna do trig stuff next week too, so. We're looking for, at the rate the biomass is increasing. So the question is how do you figure out mass? Total mass.
Mass per fish times the amount of fish.
Yeah, it's the average mass times the number of fish. So it's fish times mass. You now have a product. So we now can do our product rule. Because we're looking for the rate of change, so we're looking for the derivative. Yes. So what is our fish? Is 820. Our f prime, the derivative of fish is 50. The mass is, and the mass prime is, or the derivative of that is 0.14. So we would,
That, how would that change if it was like, it doesn't matter if it was like, one or down each year?
well, as long as the units are the same. So like we're looking at 50 guppies per week. So the rate at the other one has to be in weeks.
Oh.
If one was in weeks and one was in years, then we would have had to convert them
Okay.
to be the same. So we do 820 times 0.14 plus 1.2 times 50. Add them together, you get 174.8 grams per week.
You got what?
174.8. Not necessarily guppies, but anybody know how they actually determine the population of fish in a lake? So it is random sampling. What they do is they go in a lake and they'll tag, say, 100 fish. All right, they'll catch fish, they'll tag 100 fish. And then they go around a few weeks later and they catch a bunch of fish. They figure out how many are tagged in their catch, and they figure out how many are not tagged. So say I've got 2 that were tagged and 100 or 98 that weren't tagged. So then they can use that to determine the population in the entire lake. along with this question, if they also then weighed them to figure out the weights, they can figure out how much they're growing and how much the mass is changing. They would want to know that so this way they can do for fishing licenses. Okay? They don't want to have people overfish because then you kill the population, or overhunt because they kill the population. So they use stuff like this to determine how many hunting licensing, how many fishing licenses they give out, how many fish you can catch. There's all those rules in place to prevent you from just totally wiping out the population.
Do they do the same thing for like sharks and dolphins?
Yep. They do the same thing for crabs too. So if you ever watch the show Deadliest Catch, they actually shut down the red king crab because the population was so low that they decided that they were not doing that fishery for a few years to allow the biomass to come back, basically. So, and that cost them a lot of money and raised the prices of crab. So you can start to see how people really actually do use this stuff to calculate things that do impact our lives on a daily basis. It's not just annoying things that math teachers make you do. Well, it is annoying that we make you do it. There's an actual reason behind it. They do the same concept though. They actually have them go out and drop pots to collect crabs. And depending on the number of crabs they get, they knew what they were getting before and they could figure out the average of the population down. Yes. Everything's an estimate. It's based on, because you can't count it totally. So they use statistics to do it. So in 2020, what happened, other than the fact that the world shut down and crap happened in 2020, what was the one thing that happened in 2020 that will happen again in 2030? No. The census. All right? Every 10 years, we are required to do what's known as a U.S. Census. Okay? That is a count of every single person in the entire United States. Okay? So you're talking about how hard it is to count crabs. We are required by the Constitution to count the population every 10 years, which means count every single person in the entire country. Which means that's why they send out letters to your house to actually have you fill out how many people are there and stuff like that. They actually then have census people that have to go out and literally, if you don't fill it out, they come to your house, they ask you questions. They go through and they count like the homeless population, everything else. However, it's not, the problem is because our population's grown, it's just not very accurate anymore. So there's actually a lot of people pushing to eliminate the census and do more of a statistical analysis to figure that out. That's how people can say, like if I search Google right now, population of the United States.
Do they do that everywhere, or are there some places in the world that use
There's some people in the world that use like statistics and stuff like that to do it. It's not everywhere. So because they care for representation.
Oh yeah, because we get representatives based on how many people we got.
Right. So if we look at that number right there, they said as of January 1st, 2023, that's the number of people. Notice what it says in front of that. Estimated. That's a statistical analysis. That's not exact. Okay? Because they use that based on the number of births and number of deaths and stuff like that that are there so they can estimate it. Yeah. And then they have those records as long as it's reported. They have those records. So, but our population representation is based on that. So Connecticut used to have 7 representatives in the House of Representatives. We now only have 5 because our population has decreased compared, not necessarily gone down, but increased at a slower rate than other states were doing. So they got more representatives than we do. That impacts our representation in Congress. That impacts the number of votes for the Electoral College that we get towards the president. That impacts a lot of things. So that's all because of population. So that's why it's so important that every 10 years we have a count and we get that information that's accurate. So they just want your money.
Right.
So, but that's why, like, there's people's jobs who do this. And these jobs actually make really good money. And yes, they're complicated, but because they're complicated, they make good money. So these are the types of jobs that look into. And most of them are actually our office jobs or jobs that you can literally do working from home now. So they're not like retail jobs where you're busting your ass for $15, $20 an hour. And like, these are white collar office jobs that make $150,000 a year. So things to look into. All right, so we are done with the quotient and the product rule. We are done with class.